Welcome to the deep dive. Today, we're stepping into a truly revolutionary arena, quantum computing.
Absolutely fascinating field.
You've likely heard it whispered about, maybe seen some headlines, but what's really going on? What's the core of this buzz?
Yeah, there's a lot of excitement, definitely.
So we've navigated a detailed report. It's called quantumcomputing.pdf, and it really maps out the history, the basic ideas, the tech itself, and where it might be heading.
It's a good overview, covers a lot of ground.
And our goal in this deep dive really is to pull out the most important bits for you, give you a solid handle on this pretty complex field without, you know, getting totally lost.
Trying to make it accessible, yeah.
Prepare for maybe some aha moments because we're exploring a way of processing information that's just fundamentally different from the classical computer you're probably listening on right now.
Completely different paradigm.
We're talking qubits, this kind of magic of being in multiple states at once superposition, that is, and this almost spooky connection between them called entanglement.
Exactly. At its heart, quantum computing harnesses the seemingly strange but really potent rules of quantum mechanics to manipulate and process information.
Strange is a good word for it.
It is. And the fundamental shift to understand right away is how different it is from classical computing. Your everyday devices, they run on bits. Simple, 0 or 1, on or off.
Right, black and white.
Pretty much.
Right.
Quantum computers, though, use qubits. And here's where it gets really interesting for you. A qubit isn't just stuck being a 0 or a 1.
Okay.
It can exist as both simultaneously. That's superposition. Think of it maybe like having a dimmer switch instead of just that simple on-off.
Ah, okay, so it could be partially on, partially off, somewhere in between.
In a sense, yes, a combination of states, and then there's entanglement. This is a truly bizarre quantum link between qubits.
The spooky action.
That's what Einstein talked about. Once entangled, the state of one qubit is instantaneously linked to the state of another, no matter how far apart they are.
Instantly.
Yeah. Instantly. It's like flipping one of those dimmer switches instantly affects another one, maybe clear across the room or even further. These unique abilities, superposition and entanglement, they open the door to calculation speeds that are just, well, they're beyond reach for even our best supercomputers today, but only for certain types of complex problems.
Okay, let's try and unpack this for our listeners. So this superposition, it's like that dial, it can be anywhere between 0 and 1, not fixed, until we actually measure it, look at it.
That's a good way to think about it. The measurement forces the choice.
And entanglement is this weird connection where if one dial settles on a value, the other one instantly reflects that, maybe mirrors it or opposes it.
You've got it. That's the essence.
The report mentions this quantum approach could be a game changer, maybe early on in areas like cracking codes, cryptography,
Wave one.
designing new medicines, so drug discovery, and finding the best answers to tricky problems across different industries. Optimization, why those areas specifically? What makes them ripe for quantum?
Well, you hit on it earlier. That interconnectedness through entanglement and the ability to explore many states at once with superposition, it allows for a kind of parallel processing that's fundamentally different.
Okay.
So instead of trying one solution then the next, like a classical computer often does, a quantum computer can explore, effectively, vast numbers of possibilities simultaneously.
Right, like checking all the doors at once instead of trying keys one by one.
Exactly. And if we connect this to the bigger picture for you, the journey to get here has a fascinating history. The report points out it really started way back, early 20th century.
With Einstein and Bohr.
Yeah, physicists like them grappling with how atoms and light behaved in unexpected ways. That's where quantum mechanics itself came from. So these weren't just abstract ideas, they were trying to figure out reality itself.
So it's important for us to realize quantum computing isn't some brand new sci-fi idea. It's actually built on what? A century of fundamental physics research.
Precisely. A long road. But the field of quantum computing, as we think of it today, that really started to take shape more in the 1980s. There was theoretical work by David Deutsch.
What did he show?
What's fascinating for you to know is that he proved, theoretically, that a quantum computer could simulate any physical system much more efficiently than a classical computer ever could. That was a foundational idea.
Okay, so simulation was an early target.
It was. Then came the real shock waves. In the 1990s, 1994, Peter Shor develops an algorithm.
Shor's algorithm, I've definitely heard of that one.
You probably have. It showed a quantum computer could factor very large numbers exponentially faster than any known classical algorithm. Now, why should you care?
Because our encryption relies on that difficulty,
Right,
right?
exactly. The security is so much of our online communication, banking, data, relies on the fact that classical computers find it incredibly hard, practically impossible, to factor these huge numbers used in encryption keys. Shor's algorithm basically showed a potential way to crack that wide open.
Which, as the report emphasizes for us, has just massive implications for online security. It wasn't just a minor speed up, it was a fundamental game changer, potentially making current methods obsolete.
A huge potential vulnerability, yes. And then just a couple of years later, 1996, Grover came up with his algorithm.
Grover's algorithm.
Right. It offered a significant speed up, not exponential like Shor's, but quadratic, which is still a big deal for searching through unsorted databases.
Okay, maybe less dramatic than breaking encryption, but searching databases. We do that all the time.
Constantly. Think
Mm.
about searching huge data sets for specific information, scientific research, logistics. It has incredibly broad potential applications for many real-world problems. What stands out to you as significant about this historical path?
For me, I think it's how those huge theoretical leaps then created the challenge, right? They paved the way for the actual technology. It wasn't enough to just have these amazing ideas on paper. Scientists and engineers then had to figure out, okay, how do we actually build something that can create and control these incredibly fragile quantum states?
The engineering challenge is immense.
And the fact that now, like the report says, we're seeing major universities, big tech companies pouring serious money into this in recent years, that really tells you it's moving from theory towards something, well, tangible, hopefully.
Absolutely.
Mm.
And as we think about how these theories translate into actual computing power for you, we need to maybe revisit those core principles just a bit more.
Okay.
We mentioned superposition, that amazing ability of a qubit to be both 0 and 1 at the same time. Think about how that just massively expands the information you can encode and process compared to a simple bit.
Right. Instead of just one value, it holds a whole range of possibilities.
Effectively, yes, instead of exploring potential solutions one by one, a quantum computer can, in principle, explore a vast number of them in parallel.
So for us, it's like, remember that detective analogy? A whole team investigating different leads simultaneously, not just one detective going lead by lead.
That's a good analogy. And then there's entanglement, this deep, instantaneous connection between qubits.
The spooky action.
The spooky action, yeah. Einstein famously called it that. And it really captures how weirdly counterintuitive it feels. But this entanglement is absolutely crucial for things like quantum communication and potentially creating truly unbreakable encryption methods for the future.
The report also briefly mentioned something called wave-particle duality. Is that something we really need to get into for this overview?
For today, I think it's more about just acknowledging that at the quantum level, things don't behave like our everyday objects. They can act like particles, like little billiard balls, and like waves, like ripples on a pond, depending on how you observe them.
Okay, so just another layer of quantum weirdness.
Exactly. It just reminds us the rules are different down there. But what's maybe most crucial for you to grasp, thinking about computation, is this idea of measurement and collapse.
Right, you mentioned that. When you look at it,
Exactly. When we look at or measure a qubit that's in that superposition state of 0 and 1, it doesn't stay like that. The act of measuring forces it to collapse into a definite state, either 0 or 1. It's like, flipping a coin. While it's spinning, it's neither heads nor tails, but once it lands, it has to be one or the other.
okay. So there's this inherent element of probability involved for us. You don't always get a single definite answer, like with your laptop. You might have to run the quantum calculation many times to build up a probability to get a statistically likely answer.
That's often the case, yes. It's probabilistic computing in many ways. Now, when we talk about how these principles are actually used to perform calculations for you, the main framework people use is the quantum circuit model.
Quantum circuit model, okay.
Think of it as analogous to building with logic gates like A and D, or NOT gates, in classical computing. But here, we're using quantum gates that operate on qubits.
And these quantum gates can manipulate the superposition and entanglement.
Precisely. They can put qubits into superposition, entangle them, rotate their states. Mathematically, you can think of these gates as unitary matrices acting on the qubit states, smoothly changing the probabilities of measuring 0 or 1.
And these quantum gates, they can do things that regular logic gates just can't manage, right? They're the tools that unlock that quantum power.
Exactly. They leverage the quantum phenomena, and those algorithms we talked about, Shor's for factoring, Grover's for searching, they're essentially specific sequences of these quantum gates, carefully designed and applied to a set of qubits.
So the algorithm is like the recipe, and the gates are the cooking steps.
That's a nice way to put it. The power comes from how these cleverly designed sequences use superposition and entanglement to explore that huge computational space much more efficiently than classical algorithms can for specific problems. The report also briefly mentions a couple of other models, like adiabatic and topological quantum computing.
Adiabatic and topological, those sound a bit more specialized.
They are, yeah, more niche perhaps, or tackling different aspects.
Yeah.
The adiabatic model, for instance, is more focused on finding the lowest energy state of a quantum system. You kind of gently guide the system, and its final lowest energy state often corresponds to the solution of a particular optimization problem.
Like letting a ball roll gently down into the bottom of a valley.
Pretty much.
Mm.
So it's naturally suited for certain optimization tasks. Topological quantum computing, that's different again. It aims to create more robust qubits by encoding the quantum information in the shape or topology of the system, making them inherently less prone to certain kinds of errors or noise from the environment.
Ah, so focused on stability and error reduction.
Which is a huge issue, yeah. And that leads us nicely into where the technology is right now. The report points out some very recent progress, like NTT Research's quantum oscillator network.
Right, that cyber CIM thing.
Yeah, designed specifically for those complex optimization problems. That was just late 2022, which really highlights how fast things are moving, or it's changing.
It really is evolving quickly.
It is. And that system is interesting because it's an example of how quantum-inspired ideas can sometimes be implemented on classical or maybe hybrid systems to tackle some of these tough problems, even without a full-blown universal quantum computer.
Okay, so quantum thinking can be useful even before we have perfect quantum hardware.
Sometimes, yes. The report also rightly emphasizes the huge investments we're seeing. Governments, major corporations, the U.S. National Quantum Initiative, big funding in Germany, India. It really signals a serious global push.
It does feel like a global race, almost. But the report also stresses the need for collaboration across different industries. Why is that so crucial right now?
Well, because the field is still relatively young, scientifically speaking, and the challenges are just enormous.
Right.
By different groups working together, academia, industry labs, government agencies, they can pool resources, share crucial knowledge, avoid duplicating costly efforts. It just makes sense.
Fosters a more unified approach.
Exactly. And helps tackle both the deep science questions and the really hard engineering problems. This collaboration can also help figure out which applications are most promising in the near term and maybe share some of the significant financial risks involved in this kind of long-haul R&D.
Makes sense. And despite these hurdles, the report does sound, well, optimistic that practical, useful quantum computers might be within reach in the next decade or so.
There is optimism, yes, largely driven by progress and research on fault tolerance, basically. How to handle and correct the errors that inevitably creep in.
That's encouraging. But let's be real, there are still major obstacles. The report is clear about those, too. Error rates and this thing called decoherence seem critical. Can you explain for us why they're such big hurdles?
Yeah, decoherence. We touched on it. It's essentially the enemy of quantum computing. It's the loss of those delicate quantum properties, the superposition, the entanglement, because the qubits interact with their environment.
So the outside world messes them up.
Basically, yes. Even tiny vibrations, temperature changes, stray electromagnetic fields, any little bit of noise can cause a qubit to lose its quantumness.
And then it just acts like a regular bit.
It starts to, yeah.
Mm-hmm.
And the quantum advantage just evaporates. This leads directly to errors in the calculation. Think of trying to balance, I don't know, a spinning top perfectly on its point. Any tiny nudge sends it wobbling or falling over. Qubits are incredibly sensitive like that.
That's a great way to visualize it for us.
Yeah.
So, to fight these errors, researchers are working on quantum error correction codes. How do those work? Why are they so much harder than fixing errors in my laptop?
It's much, much trickier. In classical computing, error correction often involves redundancy, adding extra bits to check the data. You can read the bits, check them, flip them back if needed. Simple enough.
Okay.
But in the quantum world, remember the measurement problem. If you directly measure a qubit to check if it has an error, poof, you collapse its superposition. You destroy the very quantum information you're trying to protect.
Right, the act of looking changes it.
Exactly. So quantum error correction needs much more sophisticated indirect techniques. Often, it involves encoding the information of one logical qubit, the one you actually want to compute with, across many physical qubits.
So you need lots of physical qubits just to make one reliable one.
That's the current reality, yes. The report rightly points out this is very resource intensive. You might need hundreds, thousands, maybe even more physical qubits to create a single, high-quality, error-corrected logical qubit. That drastically increases the hardware demands, the complexity, the cost.
Wow, okay. And then there are other challenges too, like just getting access to the hardware and maybe funding being a bit scattered.
Those are real issues too, yeah. Access to the most advanced quantum hardware is still limited, and coordinating funding effectively across different agencies and countries remains a challenge.
So it's not just about cramming more qubits onto a chip, it's about engineering much better, more stable, error-resistant qubits and building the whole ecosystem, the algorithms, the error correction, the collaborative structures to support it all.
That sums it up really well. It's a multifaceted, grand challenge.
Okay, but despite these significant challenges, the potential payoff, the real-world applications, that's what gets everyone excited. The report highlights several key areas where quantum computing could just totally change the game for us. Let's start with material science. What's the big hope there?
Well, in materials science, the dream is to simulate how molecules and materials behave at the quantum level with really high accuracy. Classical computers struggle massively with this because quantum interactions are just too complex.
Right.
A quantum computer could potentially model these interactions accurately. This could let us discover entirely new materials, design them atom by atom with properties we can barely even imagine today.
Like what kind of properties?
Imagine, say, superconductors that work at room temperature. That would revolutionize energy grids, electronics, everything. Or designing new catalysts for chemical reactions, making industrial processes much more efficient. Or novel nanomaterials with unique strength or electrical properties that could really transform manufacturing, energy, electronics.
Wow, okay, that alone is huge. And what about healthcare? The report mentions things like near-instant vital monitoring, even creating perfect digital twins of patients to test procedures on. That sounds like something out of Star Trek.
Yeah, perfect digital twins might still be a bit futuristic, but the potential is enormous. Imagine highly accurate simulations of an individual patient's biology. Doctors could test different drug regimens or virtually practice complex surgeries on your digital twin before touching the real you.
That would be incredible for personalized medicine and safety.
Absolutely. And thinking about drug discovery, quantum computers could simulate how potential drug molecules interact with targets in the body, like proteins, with far greater accuracy than we can now. This could dramatically speed up the process of finding promising new drug candidates, cutting down years and huge costs from the current trial and error approach.
So faster, cheaper, better drugs. Okay, that's compelling. And then from the tiny scale of molecules, the report jumps to aerospace and satellites. How could quantum help there? We're talking optimizing satellite paths, secure communications, maybe even propulsion.
That's right. Think about optimizing the orbits and coordination of huge satellite constellations for communication or Earth observation. These are incredibly complex logistical problems.
Okay.
Quantum optimization algorithms could potentially find much better solutions. Or designing more efficient trajectories for spacecraft going to Mars or beyond. Again, complex optimization. And then there's quantum cryptography for secure satellite communications, making them essentially unhackable by conventional means. Even advanced propulsion concepts might benefit from quantum simulations.
So better navigation, secure comms, maybe faster travel, big implications for space exploration and national security.
Definitely. And it's not just these super high-tech areas. The report points out that everyday industrial optimization, think manufacturing schedules, logistics, complex supply chains, could see huge efficiency gains. Using techniques like quantum annealing or algorithms like QAOA, quantum approximate optimization algorithm. It's another approach for tackling these hard optimization problems. The idea is finding better ways to schedule factory floors, route delivery trucks, manage inventory, leading to less waste, lower costs, better use of resources across industries that affect all of us. Absolutely. These are exactly the kinds of complex problems, with tons of interacting parts where quantum approaches could find solutions that are just too hard, take too long for classical computers to find. And finally, the report loops back to cybersecurity.
Right, the double-edged sword we mentioned.
Exactly. While quantum computers threaten today's encryption methods, like RSA.
Which Shor's algorithm could break.
Potentially, yes. The same principles of quantum mechanics also offer the basis for new, much stronger forms of encryption. Quantum key distribution, for example, relies on quantum properties to ensure secure communication.
So quantum computers create a problem, but quantum physics also offers the solution.
In a nutshell, yes. It forces us to develop quantum-safe cryptography. Looking ahead then, the report points at key research directions. Machine learning is a big one. Can quantum speed up AI? Optimization, obviously. Those complex simulations we talked about. And critically, hammering away at better error correction.
And the hardware focus seems to be shifting maybe less on just proving quantum effects and more towards practical, reliable machines.
Yes, exactly. The push is increasingly toward building robust, stable systems that can actually run these algorithms reliably and solve useful problems. The potential economic impact, as the report notes, is just enormous across so many sectors: pharma, automotive, finance, logistics. Estimates range wildly, but we're talking hundreds of billions of dollars in potential value.
300 to 700 billion, the report mentioned. That's staggering.
It is. And think about integrating quantum with other tech like IoT, Internet of Things. The potential gets even bigger. So the market is projected to grow significantly, lots of investment.
Mhm.
But, and it's a big but,
Mhm.
we have to keep remembering those challenges.
T-coherence, error correction, scalability, actually building large enough machines and making sure everyone keeps collaborating effectively.
Those are the key hurdles still ahead.
Okay, so as we wrap up this deep dive, the main takeaway for you, our listeners, is that quantum computing isn't just a faster computer. It's a fundamentally different way of processing information.
Paradigm shift.
A paradigm shift, exactly. It holds the potential for truly transformative breakthroughs across, well, almost everything: science, medicine, industry, security.
The potential is vast.
But while the progress is undeniable and exciting, those significant technical challenges, especially around errors and scale, are still very real and need solutions before we see widespread impact.
Absolutely. It's a marathon, not a sprint.
Yeah.
But the potential applications really are incredibly significant for our future.
Indeed. It's a field just brimming with potential, and we've really only scratched the surface today, but hopefully given you a sense of the core ideas and why it matters.
Hopefully, yes.
Mhm.
The key message for you is really the sheer power that could be unlocked by harnessing these quantum rules for computation.
And on that note, here's a final thought for you to maybe chew on. Considering the immense computational power we've discussed, power that could simulate reality at its most fundamental level, what kind of entirely new scientific discoveries or technological innovations might become possible that we literally can't even conceive of today? What completely new doors might quantum computers open? Thanks for taking this deep dive with us.